So remember that massive underwater volcano, the one in Tonga, the eruption last year? Well, get this. Turns out it's been having some pretty unexpected side effects.
Yeah, it's been causing quite a stir, literally, rippling effects all the way up to the stratosphere.
And impacting the ozone layer.
Exactly. It's a complicated story, though. To really get what's going on, we need to remember that the ozone layer, well, it's not just some static thing. It's always changing, always in flux. Natural processes can affect it. And, of course, human activity plays a role, too.
Right, that makes sense. Okay, so for anyone listening who maybe needs a little refresher, could you give us a quick explanation, like, why is the ozone layer so important? I feel like most people have heard of it, but...
Yeah, absolutely. Okay, picture this. Way up high, above the Earth, there's this layer of the atmosphere called the stratosphere. And that's where we find this, well, you could call it a delicate shield made of ozone gas. Now, here's the thing. Ozone itself down here on the surface, it's not exactly something we want around.
Yeah, we're talking about smog, right?
Exactly. Ground level ozone, that's pollution. But up in the stratosphere, it's a whole different story. Up there, ozone, it's essential. It's like, you know how important sunscreen is?
Protecting us from those harmful UV rays, yeah.
Exactly. Well, the ozone layer, it acts like the Earth's own natural sunscreen. It absorbs most of the sun's harmful ultraviolet radiation. Without it, life on Earth, let's just say it wouldn't be a picnic.
It'd be, well, impossible.
You got it.
Okay, so we've got this super important shield protecting us. But now we're talking about a hole in it. What's the deal with that?
Right. The ozone hole, it's a catchy name, but it's not really a hole in the way we usually think of it. It's more like a thinning, you know, a severe depletion of the ozone in certain areas, mainly over Antarctica. And unfortunately, we humans, we've had a hand in that. A lot of the blame goes to these man-made chemicals, chlorofluorocarbons, or CFCs for short.
CFCs, right? Weren't those in like everything a few decades ago?
They were everywhere. Refrigerators, air conditioners, spray cans, you name it, and that's part of the problem. They were so common. The tricky thing about CFCs is they're stable, like really stable.
Meaning they hang around for a long time.
Exactly. They can linger in the atmosphere for years, slowly making their way up to the stratosphere where the ozone layer is. Imagine them like, well, sleeper agents, quietly infiltrating and causing trouble over time.
Okay, so let's talk about what happens when these CFCs, these sleeper agents, reach the stratosphere. What goes down up there?
So they reach the stratosphere, and that's where they encounter ultraviolet radiation from the sun. And that's what breaks them down, releasing chlorine atoms. And here's the thing about chlorine atoms. They're not very friendly to ozone molecules.
Not friendly.
Not at all. You see, a single chlorine atom, it can destroy thousands upon thousands of ozone molecules. It's a chain reaction, really. The chlorine reacts with ozone, breaks it apart, and then, well, it's free to go do it again and again. This whole process happening on a massive scale, that's what leads to this ozone depletion we're talking about.
Okay, that makes sense. But I'm still wondering, we're talking about this depletion happening all over. So why is it most dramatic over Antarctica? Why there? Why this ozone hole?
Ah, good question. So the Antarctic ozone hole, it forms because of, well, a really unique set of weather conditions. During the long winter months down there, it gets incredibly cold and dark, right?
Right, like 6 months of darkness, isn't it?
Yeah. And during that time, this vortex of extremely cold air, it just swirls around the South Pole, and it traps the air above the continent. It's like
a giant swirling freezer down there?
Exactly. A chillingly accurate description, you could say.
Okay, so that explains the extreme cold part, but what does that have to do with the ozone?
Well, inside the super cold polar vortex, you get these unique clouds forming. They're called polar stratospheric clouds. And these clouds, they're key because they provide the perfect surfaces for those chlorine atoms we were talking about. The chlorine atoms released from the CFCs, they do their ozone-destroying work even more effectively on the surfaces of these clouds.
So it's like a 1-2 punch. You've got the long-term impact of the CFCs themselves, but then you've got this extra boost from the specific atmospheric conditions over Antarctica.
You got it. It's all these factors coming together in a perfect storm, unfortunately. And, you know, just to make things even more interesting, the ozone hole, it tends to peak in size during the southern hemisphere spring. Just as the sun's rays are returning, life below is waking up, and it's at its most vulnerable.
Talk about bad timing. So it's this complex interplay of factors that makes the ozone hole such a concern. And we'll talk about those concerns more when we return, but I think this is a good place to take a quick break. All right, so before the break, we were talking about the ozone hole, all the factors that contribute to it, kind of a dire situation. But you did mention a glimmer of hope, something about the Montreal Protocol.
Right, the Montreal Protocol. It's actually a really remarkable story. It's a great example of what can happen when the whole world actually comes together to tackle a problem, a global environmental threat.
In this case, the threat to the ozone layer.
Exactly. So back in 1987, they signed this international treaty, the Montreal Protocol, and the goal was to phase out the production and use of these ozone-depleting substances, the CFCs we were talking about.
And they were in everything back then, as we said.
I know, right? So phasing them out, that was a huge undertaking, but, and this is the amazing part, it wasn't just a few countries who signed on, it was practically everyone. It was practically universal participation.
Wow, that's really something.
Yeah.
It really shows how seriously they were taking the threat. But I can only imagine phasing out chemicals used in so many products. Like, how do you even begin to do that?
Well, the Montreal Protocol, it took this multi-pronged approach. So they set firm deadlines for phasing out CFCs and these other harmful substances. But, and this was crucial, they also recognized that, developing countries might need some help with this whole transition, right? So the treaty included provisions for financial and technical assistance to help countries make the switch to, what they call ozone-friendlier alternatives.
So it was this combination of firm action, but also this spirit of global cooperation. That's really cool, actually. And what's really amazing is that it seems like it's actually working.
It really does. The data is really clear on this. There's a direct connection between the implementation of the Montreal Protocol and this decline in CFCs in the atmosphere. And as those CFC concentrations have gone down, we've been seeing some really encouraging signs that, that the ozone layer is actually starting to heal.
Well, that's fantastic news.
It is.
But I'm remembering now, we were talking earlier about how the 2023 ozone hole, it actually started forming earlier than usual. And if CFC levels are going down, why would that be?
It's a great question, and it just goes to show how complex this whole system is. It's not always a straight line. You remember that massive volcanic eruption in Tonga we were talking about?
Oh, right, at the very beginning.
Yeah, well, that eruption, it injected millions of tons of water vapor directly into the stratosphere.
Wow, I did not realize that. Water vapor, so what, does that destroy ozone directly?
No, not directly, no. It's more indirect. You see, water vapor, it enhances the chemical reactions the reactions where those chlorine atoms from the CFCs, they break down the ozone molecules. Think of it like throwing fuel on an already smoldering fire, The eruption, it intensified that ozone depletion process.
So even though we're making progress, thanks to the Montreal Protocol, nature can still, throw a wrench in the works.
Yeah, you could say that. It just highlights how important it is to keep monitoring the situation.
That's where organizations like, what was it, the Copernicus Atmosphere Monitoring Service?
Yes,
CAMS, right? And NASA's Ozone Watch program.
Right, they're providing this really invaluable data. We can actually see the ozone hole forming and changing.
And scientists can track its size and the ozone concentrations, all of that.
Exactly. It helps them understand all of these factors that are influencing it, the natural ones and the human-caused ones.
And so you're saying the 2023 ozone hole, it started early. But what happened? How did it actually end up? What was the final size?
Right. So this is a perfect example of why this long-term monitoring is so crucial because, the 2023 Antarctic ozone hole, it did develop earlier than usual, most likely because of that boost from the Tonga eruption. But in the end, it actually ended up being relatively modest in size.
Oh, really?
Yeah, especially compared to some we've seen in past decades.
Oh, well, that's a relief. What happened? Did something else happen to kind of, mitigate the impact?
Well, it wasn't so much about, additional human intervention this time around. It was more like, a bit of lucky timing, atmospherically speaking.
Okay.
Yeah, scientists at NOAA, they observed these really active stratospheric weather patterns during that period. And what happened was this led to more mixing of air from lower latitudes. And air from lower latitudes, it tends to have higher ozone concentrations. So it's kind of like, the atmosphere had its own little self-healing mechanism that kicked in and partially offset the impact of those extra chlorine atoms.
Wow. It's amazing, all these complex processes we never really think about.
Mm.
So we've been talking about this whole, using that term, over Antarctica, but what about the other side of the world? What about the Arctic? Does the same thing happen there?
That's a really important point to bring up. So while the Arctic does experience some ozone depletion, it's typically not as severe or as consistent as what we see in the Antarctic.
Interesting. So both poles experience, these long periods of darkness, extreme cold, but for some reason the ozone layer behaves differently. So we were talking about how the Arctic and the Antarctic, they both have these extreme conditions, but the ozone layer, it doesn't behave quite the same way in both places. What makes the Antarctic so much more prone to that traumatic ozone depletion we see?
It's all about the subtleties, really. Remember those key ingredients for ozone hole formation, those things we talked about. You need those super cold temperatures, the polar stratospheric clouds, and these stable, isolated air masses.
Right, and they all work together to kind of accelerate that ozone depletion process.
Exactly. And the thing is, the Arctic, it does experience all of those ingredients, but not to the same extent as the Antarctic. Not in that same potent combination, and not for as long. It's the little differences that make a big difference.
So, like, what kind of differences are we talking about?
Well, for one thing, geography plays a role. The Antarctic, it's a continent surrounded by ocean, right? And that tends to really isolate those air masses down there. The Arctic, on the other hand, it's an ocean surrounded by continents, so there's a lot more mixing of the air.
Which means the ozone-depleting chemicals get diluted more.
Exactly. Plus, the Arctic just doesn't get quite as cold as the Antarctic, generally speaking. So those polar stratospheric clouds, the ones that really speed up ozone destruction, they don't form as easily or last as long up north.
So it's less likely to get that perfect storm of conditions that lead to a full-blown ozone hole like we see in the Antarctic. But didn't the Arctic actually have a significant ozone hole back in 2020? I feel like I remember that being a big deal.
You remember correctly. That was a really unusual event. The Arctic, it experienced this really unique combination of factors that year. They had exceptionally cold temperatures, and the atmospheric mixing was weaker than usual, so you had this temporary but still very significant ozone depletion event.
Like all the elements just lined up for that short period to create, well, I guess you could say those perfect conditions.
Exactly. And it just goes to show that even with the success of the Montreal Protocol, the system, it's complex. There are still these wild cards.
But we can't get complacent, is what you're saying.
Exactly. And it's also important to remember that even though we're seeing signs of the ozone layer recovering, it's not going to happen overnight. This is a long game.
Right, because those CFCs, they stick around for a long time, as you said.
They do. They're incredibly long-lived. Even though we're phasing them out, the impact of those CFCs, it lingers for decades.
So when can we realistically expect to see, a full recovery of the ozone layer?
Well, scientists are estimating it'll probably take until at least the middle of the century, maybe even later, for the ozone layer to fully recover to pre-1980 levels. It's a marathon, not a sprint. And it requires, continued vigilance from everyone, really.
A global effort for a global problem. It's amazing to think about, really.
It is. And, the story of the ozone layer and the Montreal Protocol, it's both fascinating and hopeful, I think. It shows that when we work together, when we take action, we can actually make a difference. We can protect our planet.
It gives me hope for other challenges, like climate change.
Absolutely. The Montreal Protocol, it's a blueprint for tackling those big global issues.
So as we wrap up this deep dive, what are the key takeaways for our listeners? What do you hope they come away with?
I think the most important thing is to remember that we have the power to make a difference. The Montreal Protocol, it proves that. When we act together, when we're decisive, we can mitigate these environmental harms. We can protect our planet. But it also highlights that, we need to support ongoing research. We need to support these monitoring programs. And international cooperation, that's key. We have to keep working together. The ozone layer, it's still got a story to tell.
It's a story that's still being written.
Exactly. And we all have a role to play in shaping how it ends.
Well said. Well, this has been quite the deep dive. Really eye-opening. The ozone layer, it's up there. We don't really think about it. But this just drives home the point that even these problems that seem distant, they have very real consequences for all of us.
We're all connected. That's the thing.
Absolutely. Well, on that note, we'll leave you with this thought. That thin blue line up there, that ozone layer, it's something we take for granted. But for a while there, it was a big wake-up call, a sign of how much impact we humans can have on a global scale. And while it is recovering, it's a reminder, a constant reminder, that we have to be mindful of our impact on this planet. We have to strive for sustainability and never stop learning, never stop adapting as we deal with all the complexities of the natural world. Thanks for joining us for this deep dive into the ozone layer, a story that's still unfolding.